6 times, 6 times. Human beings left this planet, walked on another world, and came home alive. The moon, we actually did that. So when people say Mars is next, it sounds reasonable, right? A bit further away. A bit more fuel, a longer trip. Same problem, just bigger. We already cracked the hardest nut in history. Mars is just the next one on the shelf. That thinking is wrong, not just a little wrong. The kind of wrong that gets people killed. I don't mean that for drama. I mean it literally. Assuming Mars is the moon, but farther. That assumption is built on instinct, and your instincts here are lying to you. The moon and Mars aren't the same problem at a bigger scale. They're different problems entirely. And the difference doesn't live in engineering budgets. It lives inside one equation, a single equation a Russian schoolteacher wrote down in 1903. By the end of this, you'll understand something that took the world's best engineers decades to reckon with. Getting to Mars is hard. Landing on Mars is really hard. But getting off Mars and coming home, that's the part where nature just says no. Let's see if it really means it. Before any of this makes sense, we need to understand what a rocket actually is. Forget the flames. Forget the crowd. At its core, a rocket does one thing. It throws stuff out the back. That's it. That's the whole secret. You heat up fuel, blast it through a nozzle, and the rocket moves the other way. Newton's third law, every rocket ever built works on that. Simple, right? Here's the catch, and it is a devastating catch. The fuel you're going to burn later, you have to carry it now. Carrying it now makes your rocket heavier. Heavier means you need more fuel to move it. More fuel makes it heavier still, which means you need even more fuel on top of that. You see where this goes? In 1903, same year the Wright brothers flew at Kitty Hawk, a Russian schoolteacher named Konstantin Tsiolkovsky wrote the equation that captures this spiral. It looks simple. It is anything but. Here it is in plain English. The speed change you can achieve equals your engine's exhaust velocity multiplied by the natural log of your starting mass divided by your ending mass. Full weight over empty weight. That's the ideal case. Vacuum. No gravity pulling against you. In the real world, gravity losses pile on top, drag piles on top. But the equation still tells you the truth. Now, most people assume twice the speed, twice the fuel. Wrong, the relationship is exponential, and exponential math doesn't care about your intuition. Let me show you what that actually means. Say your engine pushes exhaust out at 3 keV per second. Decent chemical rocket, if you need 3 chems of speed change, your mass ratio needs to be about 2. 7, meaning at launch you weigh 7 times your empty weight, lots of fuel, but workable. Now double the speed. 6 comgas, you'd guess the ratio. Maybe doubles. 5, 6. The actual answer is 7, 4. At 9 coms, the ratio hits 20. That means 19 out of every 20 kilograms at launch is propellant. The fuel alone is 95% of your starting weight, and that's before you subtract the tanks, the engines, the structure holding everything together, whatever's left for actual payload. It's a rounding error. At 12 coms, as the ratio hits 55, you're basically building a thin metal can around a lake of kerosene. This is what engineers call the tyranny of the rocket equation, and it's not a dramatic name. This one equation has shaped every rocket ever built. Picture you're driving across a desert. No gas stations, not one. You carry all your fuel with you. Fine. But gasoline is heavy. Extra weight means your engine works harder, which burns more gas. So you pack more gas. But more gas is more weight, which burns more gas, which means you need more gas for the gas. Every extra gallon gives you a little more range, but it also eats into the range you just added. Eventually, adding another gallon barely helps at all, because the fuel is mostly just carrying itself. That's rockets. Except worse, a car fights friction. A rocket has to hurl mass overboard at blistering speed just to move forward. The Saturn V, most powerful rocket ever flown, weighed roughly 5 million pounds on the pad. That number varied slightly mission to mission, but the structure was always the same. About 85% of that was propellant. The command module that actually went to the moon and came home, 3 men inside, less than 1% of the total weight. Everything else was fuel. And the tanks and engines to burn that fuel, all of it staged and thrown away along the road. That wasn't elegance. That was desperation dressed up as engineering. The equation demanded that design, not the engineers. Now let's talk about why Apollo actually worked, because this is what makes Mars so frightening. Getting from Earth's surface to low Earth orbit costs somewhere around 9 to 10 kms, roughly 9.5 for a typical trajectory. That's the hardest part of any mission. You're fighting gravity the whole way up. From orbit, the rest of Apollo, flying to the moon, landing, launching back. Getting home costs roughly another 8 to 9 kms. Add that to the 9. 5, you get 15 to 16 kilometers total, surface to surface, there and back. A monstrous number. The Saturn V could just barely do it. But the engineers got clever. The lunar module only had to work in the moon's gravity, 1/6 of Earth's, so it didn't need to be strong, didn't need to be heavy. The moon has no atmosphere, so no heat shield for landing. You could just float down on rocket thrust alone. To reach lunar orbit from the surface, you only need about 1 km. The moon's gravity is so weak it barely costs anything. The escape velocity is 2.4 km, sure, but you don't need to escape, just orbit. Just rendezvous with the command module waiting above. So they left the bottom half of the lunar module on the surface, ascended in just the top half, a tiny cabin. Barely room for 2 people, docked with the command module, threw the ascent stage away too. Every single decision was a war against mass, and it worked. Barely in some cases, but it worked. Hold on to that word. Barely, because now we're going to Mars. The first thing to understand about Mars isn't how far it is in miles, it's how far it is in consequences. The moon is 3 days away. Something goes wrong on Apollo 13. You swing around the moon. Home in 4 days battered, terrified, alive. Mars at its closest is 55 million kilometers away at its farthest, nearly 400 million, and you can't even point at it and go. Mars is moving. Earth is moving. Everything's orbiting the sun at different speeds. You launch at exactly the right moment, follow a curved path, and arrive 8 or 9 months later. 8 or 9 months. No turning back. Apollo 13 had a lifeboat. A Mars crew has the ship they're already on. On the space station, if something goes badly wrong, astronauts can be on the ground in hours. On the way to Mars, if something fails, engine, life support, power, you're hurtling through the void at tens of thousands of kilometers per hour. No abort. No safe harbor between here and there. Nothing, just vacuum. For months, people talk about this like it's a long flight to Australia, like boredom is the main concern. It isn't. But the trip itself isn't even what scares engineers most. It's what happens when you arrive. Mars has an atmosphere. You'd think that's good news. On Earth, we use atmosphere to slow things down. Parachutes, heat shields, air resistance, free deceleration. The moon has none of that. Everything there needed rockets. So Mars should be easier, right? Oh no, Mars has what engineers call the worst of both worlds. Its atmosphere is about 1% the density of Earth's. Standing on the surface of Mars is like standing 35 kilometers above Earth, 3.5 times higher than commercial planes fly, essentially nothing. But here's the thing, it's just enough to be dangerous. A spacecraft coming in at 5 or 6 kilometers, even that wisp of air generates enormous heat. You need a heat shield. You have to manage the thermal loads, but once you've slowed to supersonic, the atmosphere's done. It can't help you anymore. A parachute on Mars, no matter how big, gets you to maybe 200 miles an hour. 200 miles an hour isn't a landing speed. It's a crashing speed. So after the heat shield does its job, after the parachute does all it can, you still have to fire rockets to survive the descent. For a small robotic lander under a metric ton like Viking, this is solvable. Hard, but solvable. A human mission needs to land 20 to 40 metric tons. Crew habitat, life support, food, equipment. And the parachute trick doesn't scale. The physics won't cooperate. A parachute big enough to slow that mass would need to be hundreds of meters across. Deployed at supersonic speed in a near vacuum. We don't know how to do that. NASA estimates that for a heavy landing on Mars, every 1 metric ton you want on the surface requires roughly 20 metric tons in low Earth orbit. 20 to 1. That ratio should give you nightmares. Here's the thing though, everything I've described so far, the delta V, the heat shield nightmare, the useless atmosphere, all of that is just the problem of getting to Mars. Assume we solve it. Assume a crew lands safely. Habitat, supplies, equipment. Everything works perfectly. Now they want to come. This is where the universe laughs. Mars has 38% of Earth's surface gravity. Its escape velocity is 5, Earth's is 11. 2. In raw gravitational terms, Mars is easier to leave. But you're not on Earth. You're on a barren, frozen planet with no infrastructure, no Kennedy Space Center, no vehicle assembly building, no army of engineers, no factory down the road, no tanker trucks of liquid oxygen rolling in at dawn. Think about what it took to launch the Saturn V. Thousands of people, billions of dollars, industrial supply chains across continents. Just the liquid oxygen alone needed cryogenic plants, pipelines, pumps, storage tanks. All of it flawless so the rocket doesn't move. On Mars you have none of that. You're 55 million kilometers from the nearest machine shop, and you need to launch a rocket. Let me give you the actual numbers, because this is where it stops being abstract. Lifting a crew off the Martian surface to orbit costs somewhere around 5 kibuzes. That's the optimistic estimate. Real missions add margin. Getting onto a transfer orbit back to Earth, another 2, 3. Getting home takes 6 to 7 kilometers total. Say your return vehicle's dry mass, everything minus fuel, is about 10 metric tons. That's generous. Probably more. Now the engine matters here. A lot. The most efficient chemical combo we have liquid hydrogen burning with liquid oxygen gets you a specific impulse around 450 seconds. That translates to exhaust velocity of about 4 combos. Best case. I'm using that number to be generous if you're burning methane instead, which is what Mars-made fuel would actually be. The specific impulse drops to around 370 seconds. The mass ratio gets worse. Keep that in mind, using the generous 450-second case. The Tsiolkovsky equation gives you a mass ratio of about 4,4, call it 4,5 with some margin, so your fully fueled vehicle needs to weigh about 45 metric tons to deliver 10 metric tons of payload. That 35 metrics had to be launched from Earth, survive a 9-month cruise, landed through that thin, miserable atmosphere, stored on the surface for a year and a half without boiling off or degrading, and then work perfectly when you light the engine. And remember the rocket equation. Every kilogram of return fuel you bring from Earth needed fuel to get off Earth, fuel to carry it across space, fuel to land it on Mars. Each step multiplies the mass. Trace it all back to the launch pad. The number becomes staggering, not expensive, not challenging, bordering on impossible with current technology. And now the cruelest constraint of all, one that has nothing to do with rockets. The planets don't wait for you. Earth and Mars orbit the Sun at different speeds. Earth goes around in 365 days. Mars takes 6087. They line up for an efficient transfer roughly every 26 months, 2 years and 2 months. That's the synodic period. Here's what that means in practice. If your crew's on Mars and wants to come home, they can't just leave. They have to wait for the next launch window, depending on the mission design. That means sitting on the surface for 30 days or 500. The most efficient mission profile is called conjunction class. You fly to Mars in about 9 months. You stay for roughly 500 days. Then you fly home in another 9 months. The round trip takes 2.5 to 3 years. And that long stay isn't a choice. It's a consequence of orbital mechanics. Try to come home after 30 days, you pay an enormous delta V penalty, sometimes over a year extra in transit just to save surface time. The fuel cost explodes. Either way, your crew is on Mars for 500 days, give or take. Now think about what that actually means. 500 days on a planet with no magnetosphere, no thick atmosphere, just a thin veil of Kiao between your crew and the universe. On Earth, our magnetic field deflects most of the dangerous stuff, charged particles from the sun, high energy rays from deep space. On Mars, that shield doesn't exist. There are 2 radiation threats, and they're different problems. Solar particle events, sudden bursts from the sun, can actually be shielded against. A storm shelter inside the habitat is a real solution. Galactic cosmic rays are a different story. High energy particles from deep space. There's no practical way to block them without meters of solid shielding around your habitat, mass you can't afford to bring. And the chronic exposure from those, that's what adds up. Over a 3-year mission, cumulative exposure hits roughly 1 sievert. Here's what that means. 1 sievert is NASA's career limit for space station astronauts. The total dose they're allowed across their entire career. A Mars crew absorbs that in a single trip. The added lifetime risk of fatal cancer, somewhere around 5 to 10% above baseline. That's not a rounding error. That's a policy problem, and a biological one. If something breaks on Mars, a critical system, a medical emergency, help is 9 months away, and only if the launch window happens to be open. 4 to 6 people. A habitat the size of a couple of shipping containers. Millions of kilometers of empty space in every direction. A communication delay of 10 to 20 minutes each way. No real-time conversation with anyone on Earth for a year and a half. Submariners, Antarctic crews, space station astronauts, they've all shown us what isolation does. It degrades performance, strains relationships, warps judgment. And those missions lasted months, not years. Those people knew rescue was at least theoretically possible. On Mars, it isn't. So some very smart people looked at all of this. The 35 metric tons of fuel, the 20 to 1 mass ratio, the whole tyranny of the rocket equation. And they asked a different question. What if you didn't bring the fuel from Earth at all? What if you made it on Mars? This is called in situ resource utilization, ISRU, and on paper it's brilliant. Mars's atmosphere is about 95% carbon dioxide if you can crack that coal. Split it into carbon and oxygen, you've got your oxidizer right there in the air. If you find water ice beneath the surface, and we have strong evidence it's there in many places, you electrolyze it into hydrogen and oxygen. Combine that hydrogen with carbon, you make methane and liquid oxygen. That's a propellant combo that works. Specific impulse around 370 seconds in vacuum. Not as efficient as hydrogen, but the materials are there, and you're not carrying them from Earth. Instead of launching 35 metric tons of fuel from Earth, you send a chemical processing plant. maybe 1 or 2 metric tons. Send it ahead of the crew, let it run for a year. It slowly fills your return tanks with locally made fuel. You've broken the chain. The fuel doesn't trace back to Earth anymore. The rocket equation becomes workable. The mission becomes possible. But there's always a but in engineering. We've never done this. Not once. Not even close to meaningful scale. Dozens of robots have gone to Mars. They've driven across plains, drilled into rocks, photographed sunsets, listened for Marsquakes. Not one of them has ever made usable rocket propellant. Not at any volume that would matter. The chemistry, we understand it. In a lab you can crack soil into carbon monoxide and oxygen, electrolyze water, synthesize methane. These reactions work. But knowing a reaction works in a lab and building a machine that runs it reliably unattended for months on another planet in -80-degree temperatures with no engineer within 55 million kilometers, those are two completely different things. Going from a lab demo to 35 metric tons of fuel on Mars requires scaling up by a factor of millions. The best demonstration we've done so far, the MOXIE experiment on the Perseverance rover, a device roughly the size of a car battery. Between 2021 and 2023, it made small amounts of oxygen directly from Martian Kial. Over its whole operational life, about 122 grams, enough to breathe for roughly 10 minutes. And it only made oxygen. The full chain to make actual rocket fuel requires several more steps, none of which have been demonstrated on another planet. We built a car, battery-sized box that made 10 minutes of oxygen. We needed to fill a rocket. You do the math. It's not impossible. It might be the key to all of this. But right now, it's a plan, not a capability. So here's where we land. The total delta V for a Mars round trip, launch, transfer, landing, surface launch, transfer, home. Somewhere between 18 to 2 cars for the most efficient profile. Some architectures push it considerably higher. Either way, compare that to Apollo's 15 to 16. A few extra kilometers per second. Doesn't sound like much. But the rocket equation doesn't care about that. A few extra kilometers at the edge of what's physically possible. That's not a little more fuel. That's exponentially more fueling. From 15 to 20 kilometers can mean tripling or quadrupling the initial launch mass. The Saturn V weighed around 3,000 metric tons. A Mars mission with the same technology carrying return fuel from Earth might need tens of thousands of metric tons assembled in orbit. Nothing close to that has ever been built in space. So where does that leave us? Mars isn't impossible. The word I'd use is unforgiving. Every decision cascades into the next. Every kilogram runs through the rocket equation. Every system has to work for 3 years. No backup, no rescue. We went to the moon. That was the hardest thing our species had ever done. Mars is a different kind of hard. You don't just need a bigger rocket. You need new propulsion. You need to make fuel on another planet. You need to solve radiation exposure. You need to keep people psychologically intact for 3 years in a tin can. We solved the moon through will and money and engineering. The rocket equation was brutal, but it allowed us to solve it. Mars is the problem the rocket equation is still saying no to. Whether we figure out how to make it say yes, that's the question of the century. If this made the rocket equation feel real for the first time, that's exactly what I was going for. Because the math isn't the enemy. The math is the honest friend telling you the truth everyone else is too excited to say.